The entire world is heavily invested in battery technology, and yet we still see this. So how can this be possible? Why are we so advanced in our knowledge and yet some of those basic safety events just seem to be lacking? Well, we just have to talk about battery safety for starters. Well, if you look around, batteries are everywhere. They're in your phone, your laptop, your solar battery, your electrical vehicle, heck, even your TV remote has batteries inside. So how can it be true that some of these batteries are safe, while others just seem to cause havoc at times? Well, to understand that, we actually have to talk about what is a battery at first. A battery, just like this little guy, is just a method of storing electrical energy. And there are two main types of storing electrical energy. One is liquid electrolyte and one is solid state. Well, basically, to not go into too much detail, liquid electrolyte means that the material that connects the anode with the cathode is liquid. And solid state, on the other hand, means that that material is solid. Currently, solid state batteries are in development and they are not too popular yet, but the promises are there with regards to energy density and charge times and discharge times. There are seemingly a lot of benefits, and yet this technology is still under development and being researched. So in this video, I'm going to focus on liquid electrolyte batteries because those are effectively all the batteries that you probably know about. So inside of the liquid electrolyte type, there are multiple families of batteries. And family is something like a lead acid battery or a lithium ion battery or sodium ion battery, and there are more and more. Currently, the most common one is a lithium ion type battery. And now, this is where many people get this confused. Lithium ion is a family. It's not a battery type. It's not a battery chemistry, I should say. It's a family. A family consists of multiple battery chemistries. So inside of the lithium ion family, you have lithium titanate, you have nickel manganese cobalt, you have lithium iron phosphate, and several more. Out of these chemistries, now we are talking about selecting the correct chemistry for the application. And depending on which chemistries you select, you will get certain trade-offs. So let's talk about battery characteristics to be able to explain the trade-offs. So a trade-off would be something like, my battery is safe and yet I cannot charge it too quickly. Or my battery has a lot of energy inside and yet it will degrade over time quickly. These are the typical trade-offs that you have to make when you're selecting a battery. The most critical component of this is you understanding exactly how and why you need a battery. So how you're going to use it and why you even need it. If you know this exact use profile, if you know your application, you will be able to select the most fitting battery. Otherwise, the chances are you're just going to buy something that doesn't fit your application. And look, honestly, you cannot blame a tractor for not winning a Formula 1 race just because it's a tractor. Okay? So, looking at NMC batteries at first. NMC battery, or nickel manganese cobalt, is one of the highest energy density batteries in the entire lithium ion family. Which means that for 1 kilogram or 1 liter of battery pack, you can put a lot of energy inside of that volume. However, just like I said before, it comes at a cost. And the cost is NMC batteries tend to degrade quite quickly, and they are also considered one of the least safe chemistries in the lithium ion family. If you compare NMC to LFP or lithium iron phosphate, for example, LFP is a bit safer than NMC, and it also doesn't degrade that quickly, which means you have much more lifetime, or in battery world, cycles inside of the chemistry or inside of the pack. However, LFP, once again, the trade-off here is you don't have that much energy density as you would in an NMC battery. And then you have the third largest family, which is LTO or lithium titanate. And these batteries are notorious for how quickly they can be charged, how quickly they can be discharged, and also their safety is incredibly high. But the trade-off here is, well, the energy density is even lower than LFP, let alone NMC batteries. So you have typical use cases for each. So think about trade-offs, and most importantly, when you're selecting a battery, think about your particular application. So once you understand your application, then you will be able to select a fitting battery. For example, let's say that you want to buy a solar battery, so a battery that would collect the energy that your solar panels have obtained. What is most important in this particular application? Is it the power release that the battery can provide? Or is it maybe the fact that it is relatively small and can pack a lot of energy, and that it's safe and reliable so that your house doesn't burn down? I would assume it's actually the latter too. So what is safety, as we circle back to safety as the original topic of this video? In battery world, safety is heavily correlated to an event called thermal runaway. Now, to understand thermal runaway, we have to understand the construction of batteries. You see, this little guy, this cell, is called a battery cell because it's just a singular cell. However, if I were to connect 3 of these together, it is already considered a battery pack. Now, a battery pack, and especially in solar batteries, is monitored and protected by what's called a BMS, or battery management system. This battery management system makes sure that batteries don't overheat, that they don't discharge too much power, that they are not charged by too much. Basically, they are a protection mechanism for the batteries, and they ensure protection by continuously monitoring every single one of these cells inside of the pack. So as the BMS is monitoring every single individual cell inside of the pack, it has 2 main objectives. Objective number 1 is to make sure that all of these cells inside of the pack are equally balanced. What do I mean by that? Energy inside of every single cell should be about the same as every other cell. So if it's not the case, if one cell holds much more energy than other cells, what's going to happen is when you start discharging the battery, that one cell with the most amount of energy is also going to draw the most amount of current. And a cell can only handle that much current. And if it's forced to discharge more than it can handle, well, its temperature is going to rise, and effectively it's going to start smoking, burning, catching fire, or even exploding. And that event right there is the beginning of thermal runaway. Thermal runaway means that one cell has caught fire or has heated up to the point that it has to release the energy, and that energy is then released to the next cell and the next cell. And so this energy transfer is causing a chain reaction that is effectively unstoppable. So that is the second objective of the BMS. It wants to prevent thermal runaway. In case where one cell heats up to a certain limit, the BMS is going to notice that because it is effectively measuring the temperature levels of every single cell, and it's going to basically switch off the battery so that it makes sure the batteries is safe. So as you can imagine, for the example of selecting a solar battery, a battery that will be installed inside of your home, safety is probably very important. And thermal runaway is probably the worst event that could happen. I mean, you don't want there to be a battery fire inside of your home. So when you're selecting that solar battery, just understand the type of cell that is inside of the battery pack. Because every single cell or every single chemistry has a different thermal runaway threshold temperature. For example, NMC reaches thermal runaway at about 210 degrees Celsius. LFP reaches it at about 270 degrees Celsius, and LTO reaches it only at about 350 degrees Celsius. So it just sounds like LTO is the best option there. However, LTO cannot pack that much energy inside of the same volume as NMC could. And then again, NMC is the least safe. So it's always about trade-offs. And those trade-offs are actually dictated by something that I mentioned before, your own application. Understand exactly what this battery will be used for and take safety as a point of measure. Take safety as something important, because oftentimes people just tend to forget that batteries are an energy storage mechanism. And when you store energy, that energy can be released when a certain event happens. A certain catalyst can make a bomb explode, just like a certain catalyst can make batteries start smoking and catching fire. Once again, guys, safety is very important, also in the battery world. Just know your application. Thank you guys, and I'll see you in the next video.